Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the magnetic field intensity at an axial point of a current carrying ring. So you can see that this is a current carrying ring which is carrying a current in this sense, and we have to find out the magnetic field at this point P. Point P is situated at a distance of x from the center of the ring, and the radius of the ring is r. We know that to apply Biot-Savart law, we require a small length of wire. Therefore, we have to assume a small length of wire like that on both the sides, and this length is dl. And let us suppose that if we draw a line connecting this dl and this point P like that, so we know that this angle between dl and r will be 90 degree. Obviously, this is the cross sectional view of the ring. If I draw the front view of the ring, and if I draw the element dl on this ring like that, and if I draw the r vector which is coming out of the plane, so you can imagine that this r vector will be perpendicular to this dl. Okay, so this is a simple thing which we can imagine, and this r vector, this will be the dl vector and this will be the r vector. So they both will be perpendicular to each other. Okay, now we know that according to Biot-Savart law, dB is equal to mu naught by 4 pi I dl cross r by r cube. This is the vector form of Biot-Savart law, and hence we can conclude that the direction of magnetic field dB will be in the perpendicular plane of dl and r. So this is dl and this is r, so dB will be in the perpendicular direction of dl and r. So it would be like that. This would be dB and it would be like that, dB. Okay, and if we draw the angles, so you can imagine that this, if this angle is phi, this angle is phi, so this angle will be phi and this angle will be phi. So the component of magnetic field which are perpendicular to this axis, this is dB cos phi, it would be cancelled out. dB cos phi and dB cos phi will be cancelled out, and these components 2 dB sin phi would add up. Okay, and we know that dB is mu naught I by 4 pi, if this is r, so it would be r square, and dl cross r will be dl into cancelling r with r, and sin 90 is 1, because we have already discussed that the angle between dl and r is 90 degree. So dB will be equal to mu naught I dl by 4 pi r square, and cos phi will be equal to this distance x upon r. So cos phi will be x upon r. So dB, 2 dB sin phi, in fact this is cos phi, and sin phi is r upon r. Okay, so dB, 2 dB sin phi, or we can say that B net will be equal to integration of 2 dB sin phi, and hence we can say that B net will be equal to integration 2. dB is mu naught I dl by 4 pi r square. So it is mu naught I dl upon 4 pi r square, and sine phi is r by r. So it is r by r. And if we know that we are doing this integration with respect to small length of the ring dl, and we have assumed two elements, one dl is this, one dl is this. So the limit of this integration would be from 0 to pi r only. We would not use 2 pi r, because if one element will move pi r, then other element will also move pi r, and total distance moved by those two elements will cover the complete ring. So B net will be equal to mu naught I by 2 pi r cube and r, and integration of dl is L, and applying the limits it would be pi r. So the final expression of B will be mu naught I r square by 2 r cube. Now we know that r, small r, was under root of x square plus r square. So it would be under root of x square plus r square. So B will be equal to mu naught I r square by 2 x square plus r square to the power 3 by 2. This is the net magnetic field. And if we plot this graph, so we can say that this would not be a linear graph. Obviously this is not a linear relationship, and x at x will be 0, B will be maximum. So at the center of the ring B will be maximum, and at x is equal to infinity or x tending to infinity B will be 0. So this graph, and one more important thing which we should discuss, that the magnetic field at all the points on the axis of the ring will be in the same direction, pointing either in this direction or pointing either in this direction. So magnetic field will be in the same direction. So now let us draw the graph. So this graph would be like that. It would not become negative on the back of the ring because direction is not getting changed, and it goes like that. So this is B max, or B max is at B center, which is mu naught I by 2r, and the direction of magnetic field on the both sides of the ring will be same. And if we discuss the special cases, so the first special case is the fact that if x is 0, which means if we are at center of the ring, if we are calculating the magnetic field at the center of the ring, then it would be mu naught I r square upon 2 r square to the power 3 by 2. So it would be mu naught I by 2r. So B at center at point O will be mu naught I by 2r. Okay, and if we are finding out the magnetic field at the center, but due to this arc, which is not a complete circle, then B at O will be equal to mu naught I by 2r and alpha by 2 pi. We can proportionally divide the magnetic field into the angles. We know that this magnetic field formula is for complete ring at the center, and the complete ring has an angle of 2 pi, and if we proportionally divide and we find out the magnetic field due to an arc, then we can simply multiply this expression with alpha by 2 pi, which is the proportional length of this arc as compared to the ring. So this will be the formula. So now in the next video we are going to discuss the more problems, concept illustration problems based on the magnetic field of the ring. Thank you.